All right, so to get this video kicked off, I just want to review again with everybody that a common log is written log of x with an implied base 10. If there's nothing written there, it's an implied base 10. And a natural log was our natural log of x, which was an implied base e. And so if you think back to the last few videos you watched, everything that we talked about was a base 10 or a base e for those examples. Now we're going to deviate a little bit from it, and we are going to talk about things that aren't common logs or aren't natural logs, so bases other than 10 or e. And so the first thing we're going to talk about here is the derivative of a log base a of x. And that's going to be defined as 1 over x times the natural log of a. So we'll go ahead and we'll prove this now. And the proof is pretty straightforward. If we let y equal log base a of x, then using our change of base formula, if you need to go back and review that from college algebra, you certainly can. The change of base allows us to rewrite a log with a certain base as a ratio of logs with any base. And it's going to make sense for us to choose a base that's easy to work with and one that we know how. So I'm using a base e, which is our natural log. Okay, so I've taken this log base a of x and written it as the natural log of x over the natural log of a using our change of base. And so now I'll come over here and ddx both sides. On the left, that gives us our dy dx. And on the right, notice this right here. Maybe I'll come over with it to the side. This is the same thing as 1 over the natural log of a times the natural log of x. The reason why I think it's helpful to write like that is because this is fully a constant. The natural log of a being a constant, is going to be a constant. And so really, I'm just taking the derivative of this multiplied by our constant. So that's going to give us our 1 over the natural log of a times 1 over x, which of course is this thing right here. Okay? Now, the result here is also interesting to the effect that if we were dealing with a natural log base e, you would get the same result, right? If we put an e right here, the natural log of e is 1, so it would still give us the overall result of that 1 over x. So this is a very helpful tool in figuring out the derivatives of logarithms that do not have base e's. Okay, so for our first example here, we've got our function and we're just going to find the derivative of it. So my y prime is going to have to be found by using a product rule. So we're going to have our first right here and we're going to have our second right here. And so for the product rule, we have the derivative of the first times the second plus derivative of the second back times the first. And so derivative of the first is clearly a 1 times the second. So that would be our log base 2. And that whole thing there is to the third power. Okay? So then plus derivative of the second back times the first. Well, again, I always drop that first in there just so I don't forget about it, especially when that second is such a long derivative. So now we'll go ahead and we'll take the derivative there. We'll need to start on the outside. We're going to multiply the 3 down. We're going to keep the inside the same. And we're going to subtract 1. So that's now going to be squared. Back times the derivative of the inside. Well, now we're going to be taking the derivative of a log base 2. And so that's going to now be the 1 over the inside times the natural log of that base, which was 2. So we've got the log base 2, and so that's going to be 1 over the inside, which was x in that last derivative that I gave you on the previous screen. But our x now is going to be this function followed by the natural log of the base. But because this, again, was no longer just an x, our chain rule is going to have to go one more depth. And now we're going to need the derivative of its inside, which would be the 2x minus 2. So times 2x minus 2. So there's the derivative of the second, this part right here that's all strung out. Once again, this is just an unsimplified derivative. Just like in Calc 1, you could certainly simplify this by factoring and combining like terms, but at this point, that's just algebra, and I think you guys can handle that, but please seek help if needed. All right, so now we're ready to move on to the derivative of an exponential function that has a base other than e. So it's going to be a little different, and you can see it's that a to the x times the natural log of a. And I say other than e only because if it was e, we would obviously know what to do. But even if we didn't think that way, let's suppose this again was an e, like in the last derivative. Well, if I put my e in right there, that's just going to go away as 1 and leave us with our e to the x. So this is just a more general form now of the exponential derivative. And so let's go ahead and prove this. And the proof is going to be using what we just learned. If y equals a to the x, now if I want to rewrite this in its logarithmic form, I'm going to get log base a of y equals x. So I went ahead and I took the exponential form and converted it into its logarithmic form. Now I'm ready to go ahead and ddx both sides. And so on the left, I've got that derivative now of log base a. So that's going to start with 1 over y natural log a. So remember, it's always 1 over the inside times that natural log of a in the denominator. But now when we have to go inside for that chain rule, like on the last problem, that's going to be our dy dx. And on the right, we have a 1. So then to get dy dx all by itself, I'll multiply the y natural log a to the other side. And our y value, as defined from the start, is equal to a to the x. So if I put the a to the x in there, there sits our proof. All right, so we'll take a look at this example here where we have pi, which is our base, that's a constant, raised to the function x tan x. And so our y prime is going to be using that derivative we just came up with, where we copy that base down no matter what it is, but then we also need to include the natural log of that base, and then in this particular case, back times the derivative of the inside. So there's our a to the x natural log of a that we talked about in the last video, or last screen, excuse me. But now we have a chain rule that we need to go in a little deeper. So the derivative of that x tan x is going to be a product rule, where the derivative of the first is 1 times the second, plus derivative of the second, which is our secant squared, back times the first. And once again, there's your unsimplified derivative, which really isn't too bad considering now it's something new. I also want to mention this one in particular could also be done by logarithmic differentiation, so don't exclude that as an option when told to find derivatives. If for whatever reason you feel like that's a better approach, then you certainly could log both sides of this. You could then bring down the exponent and continue as we've done in the past, but that's certainly an option for this one as well. Okay, so now we're ready to discuss integrals of exponential functions. And with most integrals, it makes sense to start with the derivative and just kind of remind ourselves where this thing started. And so for us, the derivative of the exponential is the same up on the screen as it was just a moment ago. And to manipulate this, I'm going to do two things. The first thing I'm going to do is just move the dx to the other side. I'm also going to divide now by this natural log of a. This is a non-zero constant, so I'm going to divide it over to this side here. So when all's said and done, I'm going to have this d with our a to the x, and then we've got our 1 over natural log of a. That's me dividing it over to the other side. And then on the right, I'm going to have this a to the x dx. Okay? At which time now, I can go ahead and integrate both sides. And we know that the derivative and the antiderivative are opposites. So these two things do away with each other. And what we end up with is this integral right here, our integral a to the x dx, is equal now to this a to the x over the natural log of a. So we've got our a to the x over the natural log of a, and of course we cannot forget our plus c. And much like the last several derivatives we talked about, we are using a, implying it's not necessarily a base 10 or not necessarily a base e. But as you notice, even if this was base e, then when we take the integral of e to the x, dx, we know that we would still get this e to the x over natural log of e plus c, which is just 1 right there, giving us what we would expect, the e to the x plus c. So it's really convenient to now have these more general forms. All right, so let's take a look at the integral here. You can see that we have a base 2 on the exponential, and we've got some other stuff involved as well, which is probably going to push us in the direction of a u sub. So notice if I let u equal tangent of theta, then du would be that secant squared theta d theta, which is a perfect fit for what we have left over. So I'm going to have the integral of 2 now raised to the u du, and from what we saw on the last screen, that's going to be 2 raised to the u over the natural log of 2 plus c. Our u value was tangent, so 2 raised to the tangent of theta over the natural log of 2 plus c for our final answer. So again, nothing really difficult about it. You're just now using that form we talked about a moment ago.